Alright, today we are looking at simplifying expressions. In particular, what we're doing today is combining like terms. So this is section 1.2b. There's a lot that's jammed into chapter 1 here. Some of it should we review. Simplifying. Apparently I can't spell here today. Simplifying expressions. But we're going to try and do this in one take. So simplifying expressions, in particular combining like terms. Alright, so combining like terms. We first need to define some stuff, and the first thing we need to define is, of course, what is a term? This is a term. This is a word that I'm going to be using really frequently. A term is a variable, number, or variable and number product. Product is a word that means literally just multiplication. So we're looking at a number, a variable, or some combination of the two. So one term, for example, is 16. 16 is a number, it's a term. Normally when I'm referring to numbers as terms, I'm just going to be referring to them as numbers. I usually don't explicitly call them terms, although they technically are. X is also a term. Another term is 15x. 15x is one of our product examples. It is both a number and a variable, 15x. And if we wanted to go a little bit crazy, we could say that 5x squared times y to the third power times z is also a term. And a few things to watch out for here. Obviously, we have our two parts here, but these up here, these are our exponents. And numbers, letters, and exponents are used to distinguish between terms which are, and here's our second vocabulary word, alike. Or I'll also refer to it as just like. And these are the same variable with matching exponents. So if you're trying to figure out if we have two terms that are alike, we need to exponents. I'm struggling to spell today, apparently. First day of the week is always tough. We're looking for terms which are alike, meaning they have the same variables and exponents on those variables. So let's look at a few examples. And then we'll determine whether or not they are alike or not alike. We have 7 and 15, 2x and 8x, 3xy, and negative 5xy squared. And then finally, we have negative 9x squared, y to the third, z, and 8x squared, y to the third, z. And we need to figure out which among these are alike and which among these are not alike. The first one of these that should be obvious is 7 and 15 is alike, or I'll say they are like terms. You can add, subtract, whatever you need to with 7 and 15. So 7 and 15 can be combined because they're both just regular numbers. Now 2x and 8x, you might be tempted to say, well, the 2 and the 8 don't match because they're not the same, whereas our x's are the same, which prevents them from being like terms. But 2x and 8x are in fact also like terms. All they need to do is have the same variable, these both have an x, and matching exponents. Neither of these have an exponent listed. So 2x and 8x can be combined. For example, you could add 2x and 8x to make a 10x. Now, looking at our third one, you might say, okay, well, the numbers don't need to match exactly. So the 3 and the negative 5, that's fine. They both have an x and they both have a y, so we should be good, right? Well, no, because this one fails on the second criteria, and these are not alike, and that is because of this right here. This y has a variable, has an exponent, of 2 on it. This y does not have an exponent on it, meaning they are not alike because the 2 and the blank here, which actually stands for a 1, and we'll talk about that in chapter 6, don't you worry. But the 2 and the blank do not match up, so they are not alike. Now, if this just looked like this instead, you could say they were alike, but unfortunately that's not the case. Finally, if we look at our last example, all right, we have our regular numbers out front. They don't really do much of anything. Let's see, this is x squared, all right, that's a square. We have a 2 here as well, good. So our x's match up. Our y's, okay, we have 2 y's. This is a 3, this is a 3, that checks out too. And we have a z, the z matches, perfect. These are in fact like terms because they have the same variables, x, y, and z, with the same exponents on them, 2 and 3. And to put this another way, what we need when we are looking for like terms is that the variable and exponent must match exactly. So the x's, the y's, and the z's, we need all of them, and they need to have identical exponents. If the exponents are different at all, they do not match, even if we have all the same variables. And what should also not come as a surprise is if this had been 2y and this 2x, then it had the same variable, so they're not alike. Now the thing that's so neat about like terms, and this is what makes our like terms so special, like terms may be added and subtracted. And that's pretty much the crux of the whole thing. They can be added and subtracted. That's what makes them so useful. That's the reason why we need to pay attention to them. They allow us to simplify problems by adding and subtracting terms. Like, when you have 7 plus 15 running around, you're not going to want to just leave it being 7 plus 15 because it'll make it more difficult. You'll have to worry about a bunch of annoying stuff because the 7 and 15 are not combined. All right, so we've got a couple of examples, and then we're going to go ahead and figure out what we're doing. So our first problem, example 1. Move this up so we have a little bit more space. Example 1 asks us 3x plus 1 minus x equals 10. And we need to solve for x. But the first thing we need to do is we need to combine our like terms. Now, the way that I combine like terms, you're going to want to make sure that there's some way to determine which like terms are being combined, because sometimes you'll have multiple sets. In this one, it's pretty straightforward. I'm going to put a squiggly line, put it in green so it's extra clear, over our like terms. 3x and negative x are the like terms because they both have an x. They both have the same exponent, therefore they can be combined. Now, the important thing to remember is how many x's do we have on our negative x? How many x's minus x's are there? There's 1, because any variable that does not have a number attached to it is assumed to be a 1. This happens to be a minus 1. Now, when we combine these together, they combine just like they normally would with addition. And in particular, when you're combining x's like this, you literally just need to add their coefficients, or these numbers, out front together. In this case, we need to subtract them, because this is 3x minus 1x, which is basically asking you, what's 3 minus 1? 3 minus 1 is 2. But it's not just 2, it's 2 x's. So 3x minus 1x is 2x. And then we have that plus 1 at the end. Plus 1 just comes right down. Nothing happened to it. And we still have it equal 10. From here, this is a 2-step problem. So we now need to solve for x. And it will just take 2 quick steps. First one is we need to get our x term, our 2x alone. And we would accomplish that by subtracting 1x. Remember, this is our opposite operation. This is our inverse operations. So 2x plus 1 minus 1, and then 10 minus 1 would end up giving us 2x equals 9. And our last step, as I try to get a little bit more space on the screen, is we need to get x alone. We have a 2 times x. Remember, coefficients are always multiplication. So we need to divide by 2. Since I'm running out of space, I'll write this over here. 2x divided by 2 just leaves us with an x. 9 divided by 2 is 9/2, or you could write it as 4.5. We can't simplify 9/2. Please don't put your answer in mixed numbers. I hate mixed numbers. Okay, we have one more example, and before we go through our second example, let's summarize the steps real quick. Our steps are, once again, steps, not stems, steps. 1, combine like terms. So this is always going to be plus or minus. 2, inverse operations. So this is the point where we have negative and positive, plus and minus, and division and multiplication. So let's take a look at our last example here, example 2. In this one, we have 20x plus 3 minus 4x minus 2x plus 10 minus 7 equals 3. And I got to move this over because the problem is so dang long, it takes up the entire screen. There should be a 3 at the end. It's a little bit of a slipshod looking 3. So we need to find out which terms on our left side of the equals sign are alike and combine them. And I'm going to start by looking at 20x. All right, 20x is a number and a variable, so we're looking for the x variable ones that have no exponent on them. So we have this one. I'll underline it in green. 3, nope, that's a regular number. There's no x on it. Minus 4x, oh, we got our x's that match with the same variable. They go together. Negative 2x, oh, it's got an x on it. It matches. It goes together. And then 10, no x. Negative 7, no x. The next thing we need to do is we got to think about anything else we can combine. So I'm going to start with the first number that I didn't combine with anything else. That's our plus 3 here. All right, well, these are all spoken for, so I don't have to worry about them. 10, oh, 10 is a regular number, and minus 7 is a regular number. And we can't directly combine things that are on the opposite side of the equal sign, so we're just going to ignore the 3 for the moment. All right, so we got to combine the stuff in green that I underlined in green and circled in red. You yourself could simply underline and circle. I think that would be adequate. If you have some colors available to you, it wouldn't be a bad idea to use them. So we first need to figure out what 20x minus 4x and minus 2x make. And amazingly, these are all going to combine into a single term. So essentially what we need to do is we need to do 20 minus 4 minus 2. And using PEMDAS that we learned earlier, we need to do our addition and subtraction left to right. So first we ask ourselves, what's 20 minus 4? Count down by 4 units, 16. And then 16 minus 2 gives us 14. So we have 14x. Then we need to combine 3, 10, and negative 7. Well, I'm going to start by putting together 3 and 10. 3 plus 10 is 13. Minus 7 leaves us with a 6. But it's a positive 6 because the 13 was larger than the negative 7. So we have 14x plus 6 equals 3. And it looks like this one is not going to have a very nice answer either. From here, we're able to move on to the second part, which is our inverse operations. We need to start by getting our x value, in this case 14x, alone. And we do that by moving our 6 over here away. And since it's added, we need to do our inverse, which is subtract. So after we subtract 6 from both sides, we're left with 14x, and we have 3 minus 6. You can think of that as being a 6 minus 3. The difference between 6 and 3 is 3. And then, because our negative 6 was the larger of the two, our answer will also be a negative 3. Our last step is we need to make this 14x into just x. And we do that since this is 14 times x by doing our division. Remember, coefficients like that are always need to be divided away. Conveniently, our 14s cancel, and we are just left with x equals negative 3 over 14. Can't simplify this any further. Negative 3 and 14 share no factors. So that covers a couple of relatively challenging examples for simplifying expressions. but it'll help you a lot if you remember to combine your like terms before trying to solve something, because otherwise you'll have way too many x's, y's, or whatever your variables are running around.